For 30 years, one question decided the chip race. Who has the smallest transistor? Today, that question has a surprising answer, because the next real advantage isn't the transistor at all. It's which side of the wafer you put the power wires on. And for the first time in a very long time, Intel is ahead of TSMC on something that actually matters. It's called backside power delivery, and Intel and TSMC built it two completely different ways. One first, one harder. This is the quiet fight that could decide who powers the next generation of AI chips. Let's break down the showdown. Every chip has two kinds of wiring stacked on top of the transistors: signal wires that carry data and power wires that carry current. For the whole history of the industry, both have lived on the front of the wafer, fighting for the same space. That worked until transistors got so small that the two networks started choking each other. Power wires steal room from signal routing, and as they get thinner, the voltage actually sags before it reaches the transistor. Engineers call it IR drop, and it quietly caps how fast and how efficient a chip can be. Backside power delivery is the fix. Move the power network to the back of the wafer and connect it up through the silicon. The front is freed for signal, the power arrives cleaner, and the logic can pack tighter. It's the biggest change to chip wiring in decades, and our two contenders took different roads to get there. To see why this matters, picture the top of a modern chip. More than a dozen layers of copper wiring, finer than anything else humans manufacture. As we push toward 2-nanometer class transistors, those layers got so crowded that power and signal were competing for the same microscopic tracks. Thinner power wires mean higher resistance, and higher resistance means the voltage that leaves the package isn't the voltage that reaches the transistor. Some of it is lost as heat and droop on the way in. You can't just keep adding metal layers. Each one adds cost and complexity, and it doesn't fix the fundamental crowding. This is the wall every leading-edge fab hit at once. Backside power solves it structurally. By moving the entire power network to the underside of the wafer, you separate the two jobs completely. Signal on top, power underneath, and you shorten the path current has to travel to reach the transistor. It's like taking a building's electrical mains out of the same crammed conduit as the data cables and giving them their own dedicated shaft. Cleaner power, more room for signal, denser logic. The idea is shared. The execution is where Intel and TSMC split. Intel made the boldest schedule bet in the industry. Its version is called PowerVia, and the clever part is how it connects the two sides. Tiny vertical channels drilled through the silicon, nano through silicon vias, that carry power up from a backside network to the transistors above. Crucially, Intel de-risked it. Instead of debuting backside power and a brand new transistor at the same time, it proved PowerVia on a dedicated test chip first, so the hard new step was understood before it shipped for real. And ship it has. PowerVia is an Intel 18A, the process behind Panther Lake, which launched at the start of 2026, paired with Intel's ribbon FET transistor. The early numbers were striking, around a 6% jump in frequency at the same power, cleaner power delivery, and a chip that was actually easier to diagnose because the two networks no longer overlapped. But the real story is competitive. This is the first time in years that Intel has beaten TSMC to a major manufacturing capability, a genuine head start of roughly a year and a half to 2 years. For a foundry fighting to win back customers and credibility, being first to something this fundamental is exactly the kind of proof point it needed. TSMC saw the same wall and chose the more aggressive design. Its version is called Super Power Rail, and instead of routing power through vias that land on the chip's wiring, it connects the backside power network directly to the transistor's source and drain. No via stack in between. Electrically, that's the better answer. It strips out a layer of resistance that even Intel's approach still carries. But it is brutally hard to build. The alignment tolerances are tighter, the integration is more delicate, and analysts call it one of the most complex backside power designs anyone has attempted. TSMC is bringing it in with A16, its first angstrom-class node, targeting volume production late in 2026, meaningfully behind Intel. What is the harder road by? Compared with TSMC's own enhanced 2-nanometer node, A16 is projected to deliver roughly 8 to 10% more performance at the same power, or cut power by 15 to 20% at the same performance, while squeezing in another 8 to 10% density. TSMC's bet is simple. Be later, but be better, and let its yield machine and its enormous customer ecosystem turn a more difficult technology into the default choice for the highest-end chips. Here's why two wiring schemes are suddenly front-page material. AI accelerators are limited by exactly the two things backside power improves: how much performance you can pack in and how much power it costs. Every extra percent of efficiency at this scale is megawatts across a data center. So the node that delivers backside power best becomes the node the AI designers want. The two roads lead to different customers. Intel's 18A Euro and its refined 18AP power Intel's own chips and its foundry clients. And being first lets Intel say something it hasn't said in years. Try us, we got here first. TSMC's A16 is aimed squarely at the AI high-end, where the biggest accelerator designers are already lining up for the density and efficiency Super Power Rail promises. And this isn't even a two-horse race. Samsung is bringing its own backside power process too. The decisive factor won't be a slide showing the smallest transistor. It'll be who can deliver backside power at high yield, at huge volume, on the largest chips, because that's what an AI accelerator actually needs. So who wins the showdown? Both on different scoreboards, and the most important winner is on neither company's slide. Intel wins the calendar. It shipped backside power first, it works, and it hands Intel a real lead and a credibility reset for a foundry that badly needed one. TSMC wins the architecture. Super Power Rail is the more advanced design. It's aimed at the AI high-end. And history says TSMC's yield and ecosystem tend to turn later into dominant. If you're forced to pick, Intel has the head start. But the race now is whether it can scale that lead before TSMC's better technology arrives in volume. The deeper winner, though, is the capability itself and the people who enable it. Backside power forces new manufacturing steps: thinning and bonding wafers, patterning the back of the chip, inspecting a side of the wafer nobody used to touch. The equipment and materials companies behind those steps just gained a brand new reason to grow, no matter whose logo ends up on the chip. And the ultimate beneficiary is the AI chip designer, who gets more performance per watt without waiting for a smaller transistor. Watch yield and watch which AI customers commit, not the spec sheets. In this fight, the transistor finally stopped being the whole story. If you want the real engineering battles behind the AI chip race, the ones that decide who actually wins, not the marketing version, this channel takes them apart one at a time. This video is part of a series that follows the showdowns shaping the next decade of silicon, from memory to packaging to the wires that power the transistor. Subscribe if you want the actual semiconductor industry view. No hype, no hot takes, just how the chips really get built. Thanks for watching, and I'll see you in the next one.